Hi there, welcome to your lesson on estimating and measuring. Let's begin with this little activity. Here we have a photo of Margaret Hamilton, who worked for NASA as the lead developer for the Apollo flight software. The photo here shows her in 1969 standing next to the books of navigation software code that she and her team produced for the Apollo mission that first sent humans to the moon. Look at that giant stack of books. Your task is, number one, estimate the height of the books of code stacked together, as shown in the image. And along the way, when you're making that estimation, what assumptions are you making? Let's do an estimate in centimeters. Perhaps you estimated something similar to the height I have here, which is 165 centimeters. This, of course, assumes that she is of an average height. I looked at the coat rack beside her also to help with my estimation, but I think that's a pretty good estimate. Number two, try this estimation. Estimate the number of pages of code for the Apollo mission. So look at all those books stacked up. How many pages is that? And I don't mean back to back, just single pieces of paper. So how many pages do you think? In this case, it's kind of important to begin with, I would say, a feel for how thick one page is. And one piece of paper, a standard thickness of paper, is 0.1 millimeters in thickness. That would mean there's 100 papers for 1 centimeter. And if she's 165 centimeters, then I do 100 times 165 to get 16,500 pages. I wonder, is that close to what you came up with? Okay, so I'm moving on with still the conversation of estimation, because estimation is this kind of starting place for a lot of mathematics we do. Before we even calculate anything in our minds, we often do a quick estimate. So let's talk about estimation some more. What is estimation? How is it done? What's your response to that? Here's my thoughts on that. Estimation is the process of finding estimates or approximations. An estimate can be derived from the best information available, like we did in this photo here. We used clues around us to basically estimate how many pages are there, right? One clue was kind of working with her height, and that height allowed us to then move on to estimate how many pages there are, right? We used clues to do a good approximation. Estimation is often done by comparing the property being measured with another, and that's exactly what we did here. Okay, another question. Why are estimations useful? Why do we do this? Why make estimations? My response is estimations are useful as they can quantify unmeasurable values. If there's something that cannot be measured, well, at least we can estimate it and have a quantity to work with as we do further calculations. Also, estimates can be used to check whether calculated results make sense. So even if we can calculate something, it's good to begin with estimation, because then we can compare our calculated amount to the estimation, because often we can make errors in calculation, but checking how close it is to an estimate allows us to kind of check if our calculations are correct. Now that we've talked about estimation, let's take a step forward to measurement or measuring. Usually we begin by looking at something and estimating quantities, and then we can get to the actual work of measuring it and seeing how close actual measures are to what we estimated. So with measurement, let's begin here. Here's a question for you. What does it mean to measure a property of an object, and how do we measure? Perhaps you answered something like this. Measuring is a process of quantifying properties of an object. It helps us compare objects and understand how they relate to each other. Through measurement, we can answer questions like, how long is my room? How much water can my water tank contain? How heavy is my suitcase? In other words, measurement allows us to put numbers to the world around us. We measure a quantity by using a measuring instrument appropriate for the quantity that we are measuring. For example, to measure length, we might use a ruler. Of course, this is one of the most simple measuring tools, and there's many others for all kinds of purposes. And a second question for you. Which properties of an object can we measure? Here's a long response as well, because there's so many things that can be measured. For example, some of an object's properties are length, height, volume, weight, color, texture, smoothness, etc. A measurement is a numerical description of a property of an object. Some properties are easier to measure than others, of course. There are established approaches to measuring length, height, surface area, for example, but there are no established procedures for measuring smoothness, for example. A measure of smoothness would also depend on the person's perception of it, and thus could be very different for different people. So in other words, again, when we talk about measurement and the properties we can measure, we're always thinking about things that can be measured in a quantifiable or numerical way. Now, let's take this little challenge together. Here is a photo of a grapefruit, and you have a hand holding it to give you sort of an idea of maybe how big that grapefruit is. And we know there are different properties that we can measure. We just talked about that. So in this case, I would like you to estimate the length, surface area, volume, and weight of this grapefruit. So again, that's your challenge. Based on this image, can you estimate these 4 measurable properties of a grapefruit? Length, let's do it in centimeters. By length, I mean this distance, let's say from here to here. And surface area will be in centimeters squared. That means, imagine if you had a length here, some length, and then surface area is like how many 1 by 1 square centimeters can you wrap around this grapefruit. So if you said this was 20 centimeters, for example, then think about, okay, there's like 20 squares tall here, so how many little squares 1 by 1 centimeter can you wrap around this? That would be surface area. Volume is in centimeters cubed. In that case, you're thinking of little cubes inside the grapefruit, little cubes, and the length, width, and height of the cube are all 1 centimeter. So how many little cubes can fit in there? So again, your basic measure will be their length, and from there you can start thinking about how many squares wrap around it and how many cubes fit inside it for volume. And finally, please give a weight in grams. So remember, there are 1,000 grams in a kilogram. You can think of it that way. Let's see how close you are to the actual measures, which I will reveal very soon. All right, let's start looking at the real measurable quantities here. So first of all, I measured, like I said, from here to here on the grapefruit. I measured with a ruler, and I got exactly 11 centimeters. So notice that I took that same picture, I turned it sideways, and I put it in Desmos. And I sat the grapefruit on the axis here, x-axis, from 0 to 11, because that is the actual measure in centimeters that I got. So 11 centimeters. How close were you? Now next, surface area. Notice this blue arc here, and that's this equation here. That equation is for a half circle or a semicircle. So I'm basically putting a circle there, a half circle, and seeing if it kind of matches the shape of the grapefruit. It kind of does. And of course, our fruits like this, like grapefruits and oranges and apples, they're kind of like spheres. They're not perfect spheres, but they kind of are like spheres. So I said, hey, maybe this would be like a sphere if I put a full circle around it and made it 3-dimensional. So therefore, when I found the surface area, I assumed it's a sphere. And the surface area of a sphere is 4 pi r squared. And you can see that punched in here. 4 pi r. R is the radius. And since I said the entire length is 11, that means 11 centimeters is the diameter. That means the radius is 5.5, which is half the diameter. So that gives me this value here, about 380 centimeters squared. So by saying this is 11, I am also saying that 380 little squares, 1 by 1 centimeter, can cover the surface of this grapefruit. Interesting. There's another way to look at surface area, though, and it might be even a better way. It might be something we look at later in the course as well. So what I did here is I wrote a different function. This one is the red one. So notice here is another curve. That's a power function, kind of like a quadratic, but has a power of 4. You can see here, it might be a better match for the shape of the grapefruit than just a semicircle. Maybe slightly better. And in that case, I use this formula here for surface area. And this is a formula using this symbol here. Means it's an integral symbol. This is calculus. This integration can be used to find the surface area. And this integral equation here gives me this value. Notice it's pretty close to 380 when I assumed it was a sphere. A little bit less though. So anyway, the surface area definitely is somewhere around that value, right? Okay, just wanted to show you that because calculus is something we'll be doing later in the course. Okay, now let's move on to volume. Okay, for volume, I used Archimedes' method, or Archimedes' principle. And you may be familiar with this. This is the method of basically water displacement, right? You have some kind of container where you've measured the water level. You have the object which you want to check the volume of. You put that object in the water, like it was here, and the water level will rise. And of course, the water level will rise by the volume of the object you put in, because that object has replaced that water down there, and that water level then rises up. That's the method I used. So here's a giant container I had, and before I put the grapefruit in it, it was at about 2,000 milliliters, which is the same as 2,000 centimeters cubed for volume. Then I put the grapefruit in it like this, and the water level rose up to 2,500. So that tells me I have a volume of 500 centimeters cubed. Okay, because 500 centimeters cubed of water were displaced or moved up when the grapefruit went in. How close was that to your estimate? I wonder. Okay, and again, that 500 centimeters cubed means if you had little cubes and each cube had sides 1 centimeter by 1 centimeter by 1 centimeter, there would be 500 of those cubes inside this grapefruit. Okay, finally, the weight. The weight, I just simply put it on a little kitchen scale, a cooking scale, and you can see here just barely right there, 400. So 400 grams is the weight of this grapefruit. How close was that to your estimate? Now, another way to look at the weight is this, and this is interesting if you've done some science like this. We know water has a density of 1. What that means is water is set as the standard for density. And when something, for example, 1 centimeter cubed, which is a volume measure of water, has a weight of 1 gram, or 1,000 centimeters cubed, which is 1 liter of water, weighs exactly 1 kilogram. So that's something important to remember. 1 liter of water is exactly 1 kilogram. And that's the way humans set up these scales. So now, if you take things that have different densities, in other words, are more dense or less dense than water, or heavier or less heavy than water, then that ratio will change, right? 1 gram to 1 centimeter cubed will change. So in this case, I looked up something online. I looked up different fruits, and it says here, the average densities for different fruits. Here's apples, limes, lemons, and oranges. I decided to focus on oranges because a grapefruit is very similar to an orange. And it says the average density for an orange is 0.8 about grams per centimeter cubed. So less dense than water, right? Water would be 1. This is 0.8. So if you take our 0.8, that density, multiply it by 500 centimeters cubed, which is the volume of my grapefruit, I get a weight of 407. And notice that is very close to the weight I measured on the scale. So that density I found online for an orange is very close to the density of this grapefruit as well, which is very interesting. Not quite as dense as water, a little bit lighter, but gives me a very close measure. All right, finally, I have this question for you. How accurate, it says, are your measurements, but mine? How accurate are my measurements? Could we use different units, and would that affect my measurement? What do you think? Well, measuring always requires approximating, right? I kind of approximated the water level and this what I saw on the scale and so on. And measurements are approximations. If a smaller measuring unit is chosen, we could obtain a more accurate measurement. That means if I had a better scale, a scale that showed more detail, like tenths of grams or hundredths of grams, I could get a better measurement. Or if I had used a more sophisticated submersion technique for the volume displacement, I could get a better reading as well. So that's what this means, that as our measuring tools get better, so do our measurements. Okay, so some key conclusions about estimation, first of all. Estimation is finding an approximation as close as possible to the value of a measurement by sensible guessing. Often the estimate is used to check whether a calculation makes sense or to avoid complicated calculations. Okay, and also about estimation, it's often done by comparing the attribute that is measured to another one or by sampling. And then for measurement, a few conclusions. Measurements help us compare objects and understand how they relate to each other. We can compare things once we know how they're, the weight of one compared to another and so on. Measuring requires approximating. If a smaller measuring unit is chosen, then a more accurate measurement can be obtained. And finally, when you measure, you first select a property of the object that you will measure, then you choose an appropriate unit of measurement for that property, and finally you determine the number of units and the proper tool, of course. So this kind of summarizes the journey we've taken. Great job. We'll see you soon.